In this video, we will be talking about effective nuclear charge. We will then use the concept of effective nuclear charge in later videos to justify the trends that we see in atomic radius, ionization energy, and electron affinity. The effective nuclear charge is the net positive charge that is attracting the valence, or outermost, electrons towards the nucleus. Core electrons effectively shield the electrons in the outermost principal energy level from the nuclear charge. When you're working with electrons that have a higher principal quantum number, the N value, they are outside of the inner core electrons, those with a lower principal quantum number. Essentially, as you increase the quantum number, the orbitals get bigger and bigger and bigger. So if you have an orbital with a higher principal quantum number, it is bigger, thus the electrons are further out. So your inner core electrons, those that have a lower principal quantum number, are held within your outer principal quantum number orbitals. The outermost electrons in the valence shell do not efficiently shield one another from the nuclear charge. And so, as long as we're working with electrons with the same principal quantum number, they are not generally held closer to the nucleus, so they don't effectively mask the charge that the outer electrons feel. The periodic trend for the effective nuclear charge is that it increases as you go across the period and decreases as you go down a column or group. Electrons in the same energy level essentially do contribute to screening, but since that contribution is so small, they do not really take part in the calculation. So for example, electrons in the s orbital are better at shielding than electrons in the p orbitals, because the s orbitals tend to be smaller and closer to the nucleus, and so your p orbitals, because they're a little bit bigger, aren't as close to the nucleus and so don't really do as much shielding. But when you're in the same principal quantum number, all of your electrons are roughly the same distance. They can move away from each other, and so they're not really in between your outer electrons and the inner electrons. And as a result, do not participate in shielding. As you go across the period, you are essentially adding electrons in the same energy level, but in different orbitals. And they are getting further and further away, and so the shielding ability decreases because they are able to move further and further away from each other. Now, while you're going across the period, in terms of looking at different atoms or different elements, you're increasing the number of protons. And it is that increase in the number of protons that is increasing the effective nuclear charge. The way that we will determine the actual effective nuclear charge is by looking at two competing factors. One is the nuclear charge, which is the number of protons that we have in the nucleus, and the second is this concept called shielding. Shielding is the number of electrons in a lower energy level than the outermost electrons that you're working with. They are effectively getting in between the nucleus and your outermost electrons, and essentially canceling out the charge that the outermost electrons feel. This process of canceling is called shielding because they're shielding those outer electrons from feeling the full positive charge of the nucleus. Electrons in the same energy level do contribute to the screening, but their contribution is small and they are not part of the calculation. The trend in shielding in terms of strength is that the s orbitals, which are smaller, are better at shielding than the p, which are better than the d, which are better than the f. But when we're calculating the shielding, we count all of the inner core as the same. The effective nuclear charge, we will label that as Z effective, is equal to the charge on the nucleus minus the number of electrons that are getting between the electrons that we're currently working with, the N value of the period that you are currently filling the electrons with, and the electrons that are in the inner core. So those are the electrons, essentially, that you can think of it as the number of electrons that the nearest noble gas has. The noble gases being the far right part of the periodic table, the furthest to the right group of the periodic table, and those are when you close out a particular shell. We can get an idea of the general trends that we expect for the effective nuclear charge by looking at the two components that make it up. The nuclear charge, which is essentially the number of protons that we have in the nucleus, and the shielding, which is the inner core electrons that are closer to the nucleus than the electrons that we are currently working with. So the nuclear charge we will indicate in blue, in this light blue. So as we go across the periodic table, the nuclear charge, which is again the number of protons, will increase. For example, hydrogen has 1 proton, helium has 2. So as you go to the right, the number of protons increases, so the nuclear charge will increase. As you go down the periodic table, the nuclear charge will also increase. If we look at helium versus neon, helium has 2 protons, neon has 10. So the number of protons, which are the positive charge component of an atom, go up as you go down the periodic table, which means that our nuclear charge will go up as you go down the periodic table. For shielding, we'll use a red to indicate. For shielding, as you go across the periodic table, there is no real large change. So for shielding, this is not really applicable in terms of the change. There will be a slight increase as you go to the right, but it's not big enough that it factors into our calculation. However, as you go down the periodic table, the shielding goes up. So the shielding is essentially the inner electrons, the electrons that are closer to the nucleus than the current ones that you're working with. So let's say that we were working with something like sulfur, for example, right, and trying to figure out the shielding on sulfur, the effective nuclear charge. According to our calculation, which is the effective nuclear charge is the nuclear charge minus the shielding, our effective nuclear charge would be equal to the number of protons that sulfur has, which is essentially its atomic number, so that'd be 16, minus the shielding, which is the number of inner core electrons that it has. The way that you can get that number is just look at the previous noble gas. So that would be, in this case, neon. So neon has 10. So the effective nuclear charge on sulfur would be 6. If we move to something like silicon, this one was for sulfur. For silicon, the effective nuclear charge would be, for this one, our number of protons is 14. We have the same number of inner core electrons as we did for sulfur, which is the number of electrons that neon has, so that's 10, so that's 4. What this tells us is that the outer electrons in this row of our periodic table in our third period, each one of those is going to have 10 electrons that are effectively shielding the same number of protons from those outer electrons. So as we go to the right, our effective nuclear charge is going to keep going up and up and up. And because the effective nuclear charge goes up, it will pull the electrons more towards it, which we will see in later videos will decrease the radius of our atoms. So the net for our effective nuclear charge is it will increase as we go to the right, increases as we go to the right, and it will actually decrease as we go down. And the reason it decreases as we go down is partially because the atoms increase in size. The amount of charge that the outer electrons feel is decreased because they're getting further and further away from the nucleus. So our Z effective, as we go down the periodic table, right, is actually going to decrease a little bit, right? And that's because the shielding becomes more important than the slight increase in the nuclear charge, and so the effective nuclear charge will decrease as we go down the periodic table.